Hi, we are Naroa and Unai, and we are going to present a video about diffusion models. Diffusion models are a type of generative model that nowadays beats every other previous state-of-the-art generative model with images, like autoencoders or generative adversarial networks, and so on. So the idea of diffusion models comes from the field of statistical physics, where the first proposal was the deep unsupervised learning using non-equilibrium dynamics, but all the other proposals related to this are pretty similar in the ideas that they have underneath. So the basic idea is like we can imagine that we take an image, we add more and more Gaussian noise to it, and at some point this image would be unrecognizable. But what if we can undo this process? So we start from noise image and we gradually remove the noise and end up with a coherent image. This is the basic idea behind the diffusion models. So diffusion models are a type of generative models where we define a Markov chain of diffusion steps to slowly add random noise to the data. And then we try to learn to reverse the process of diffusion to construct desired data samples from the noise. So the process can be structured in two main steps. The first is to take an image, let's call it x0, and gradually add Gaussian noise to it through a series of t steps. This is the forward diffusion process. Then a neural network is trained to recover the original data by reversing the noisy process. So being able to model the reverse process, we can generate new data. And this is the so-called reverse diffusion process, or in general, the sampling process of any generative model. So diffusion models are basically trained to the noisy images, and therefore they can generate images by iteratively denoising pure noise. So as we can see here in the animation, we have the original image and then we add more and more noise in the forward process, and we have then a simple noise of an image, and then we try to reverse the image to recover the original image. So more mathematically speaking, let's Q of x0 be the real data distribution, so the real images where we can sample. And we define the forward diffusion process Q of xt condition to xt minus 1, which adds Gaussian noise at each time step t, according to a non-variance schedule. So this is defined by this Gaussian distribution as a normal Gaussian distribution is defined by two parameters, the mean mu and the variance sigma squared. And each new slightly noisier image at each time step t is drawn for a conditional Gaussian distribution defined by the mu of t and sigma squared of t. Which we can do here is a reparameterizing using the epsilon drawn from this normal and then setting to the xt as follows. So notice that the beta here are not constant and depends on the variance schedule. So the effect of the variance schedule can be seen here clearly. For example, the top of the part is using the variance schedule or doing linearly, and then other proposals like the Nicol and Dariwalt using the cosine schedules. So as we said before, the forward diffusion process can be seen as a Markov chain of small steps that adds Gaussian noise to the original image. So if we knew the conditional probability distribution P of xt minus 1 condition to xt, we could run the process on reverse. So sampling some random noise and then gradually denoise it, that we end up with a sample from the real data distribution x0. However, this probability distribution is untractable, so we need to know the distribution for all possible images in order to calculate the conditional probability. But we can approximate this conditional probability using a neural network model, like this defined by P of theta, where theta are the parameters of the neural network of xt minus 1 condition to xt. So we assume that the reverse is also Gaussian. Then, as a Gaussian distribution, we define it by two parameters, the mean parameterized and the variance parameterized. So we can parameterize the process as follows, using this Gaussian distribution where the mean and the variance are also conditioned to the noise level t. So our neural network needs to represent or learn the mean and the variance. However, the DDPM autos, for example, decide to keep the variance fixed and let the neural network only learn the mean of this conditional probability distribution. Later proposals have improved this, learning also the variance of the conditional probability. So as we can see here, this is what we explained before. So this is what we are trying to model, this reverse process. So how we can train diffusion models? So as a reminder, we want an objective function to learn the mean of the reverse process. So the authors have observed that the combination of Q and B theta can be seen as a variational autoencoder, and we can use the variational lower bound, the elbow, to minimize the log likelihood with respect to the ground truth data samples x0. So it turns out that the elbow for this process is a sum of losses at each time step t. And by construction of the forward Q process and the backward process, each term except from L0 of the loss is actually the KL divergence between two Gaussian distributions which can be written explicitly as an L2 loss with respect to the means. A direct consequence of the constructed forward Q is that we can sample xt at any arbitrary noise level condition to x0. So the sums of a Gaussians is also a Gaussian. And we do not need to apply the forward repeatedly in order to sample xt. Also notice that the alpha hat of t are alpha hats or t are functions of the known beta t variance schedule, and those are also known and can be pre-computed. Thanks to the nice property that we have mentioned before, that is explained more in detail in the original papers, so we can reparameterize the mean to make the neural network learn to the added noise, not the direct mean predictor. So summarizing, the training works as follows. So first, we take a random sample x0 from the real data distribution. Then we sample a noise level t uniformly between 1 and t. So this is sampling the noise level randomly. Then we sample some noise from a Gaussian distribution and we corrupt the initial image by this noise at level t. The neural network is optimized or is trained to predict this noise based on the corrupted image xt using simple mean square error between the true and the predicted Gaussian noise. Finally, we want to remark that there are a lot of applications of using diffusion models, and we have here a good survey of the methods and applications where the diffusion models are applied right now. So that's all for the presentation, and thanks for your attention.